Hello, everyone. I'm very glad to be here with my team, Konecranes, to present to you about the final result of the project that we have done. I am Phuong, the guy with the beard. My friend Olli is the guy with the sunglasses, and Aalto, our team lead, is the other one. Our project is supported by Konecranes, and we decided to call it Elasto magnetic sensor for load measurement. Can you change to the next slide? The question you might have right now is why load measurement is so important. And it's not actually an obvious thing. Let me take an example to make it clear for you. In cargo industry, when we use the cranes to lift the containers, its lifespan is affected by the mass of the containers. In fact, the lifespan of the crane is reduced drastically when the load is too high. So we really want to know how much we lift. And when the cargoes are placed onto the ship, we want to distribute them evenly to both sides of the ships in order to keep the balance right. So that's why load measurement is very important. The current method that we use to measure the load is strain gauge. But in this project, we want to explore a new approach and principle to measure the load. Our main goal is to prove that the concept can be applied in the industry. But we also wish that the method can be developed further to achieve even more accuracy and certainty than the current one. And with that in mind, I want to go through the principle that we use in our experiment. As you can see in the figure, we have two coils, which we call the primary coil and the secondary coil. They are wound around a ferromagnetic core. It is very important that the material of the core is ferromagnetic. Otherwise, this won't work. The primary coil is connected to a power source. When we allow the current flow inside it, the core will be magnetized, and the voltage will be induced in the secondary coil. After the setup becomes stable, we apply force onto the core and observe the change in the voltage in the secondary coil. And from this, we can formalize a relationship between applied force and induced voltage. And so after we got the idea, the project step become quite clear and simple. The picture on the left shows our first trial to see if the setup really worked, and it did. And the second one is the one that we actually used in our experiment. There's only one thing that I want to point out here is that we used the tensile bench to effectively apply and control the load onto the core. And now Olli will tell you more about the test that we did.
Yes, for testing our devices, we scaled it down a bit from the actual size of the crane hook, and we decided to use a 10 mm steel bar to mimic the hook shank that the sensor would be attached to. The sensing device was then wrapped around this core, and primary coil was excited using the signal generator and amplifier to act as an AC power source. For data acquisition, we used the high accuracy multimeters to measure excitation voltage and current for the primary coil and the induced voltage and its change in the secondary coil. Also, to counter the effect of the temperature change of the device during testing, we attached a thermocouple to measure surface temperature of the steel core. With the setup done, we mounted it to the tensile bench, and with that we were able to apply varying loads with high accuracy for the steel bar to study the effect of the stress to the induced voltage in the secondary coil.
Okay, so then here is a short video of testing in the laboratory. So in the setup we had audio amplifier and signal generator, which you can see here. And then here we have multimeters for primary and secondary coil voltage measurement, and the numbers are changing all the time, as you can see in the video. And here we have the multimeter for current measurements. And here you can see the temperature measurement with thermocouple, and that's connected to the multimeter down here. And here you can see increasing load curve from 10 kilonewtons to 12 kilonewtons. And that's the setup. Then about the results. So we expected the relationship between force and induced voltage to be linear, but it was not. So as you can see from the graph, we have force on the y-axis and change in the coil voltage on the x-axis. And instead of linear relationship, the equation is quite well following this second order polynomial function. So here we have the maximum absolute error about 300 newtons, and the average error percentage is 5.6, and repeatability error 0.069%. Then conclusions. So proof of concept was successful because this EM sensor can be used in crane applications when the force voltage relationship remains the same for crane capacity area. And the setup we built, the accuracy was 94.4%, which means 10.4 kilograms on average error with loads from 0 to 1,200 kilograms. And on the right hand side, you can see the actual concept of our crane sensor. So here we have 40 millimeter crane hook shank, and the sensor is 75 millimeter long. It has 1,000 rounds on primary coil and 200 rounds on secondary coil. And the hook material in this one is IC1040 carbon steel. And this kind of a setup needs approximately 90 amps to make the core saturated. Thank you for your attention, and if you have any questions, now it's time.